So in this problem, we begin by being told that we want a pendulum that has a frequency of 0.3 hertz. And it's going to be used here on the Earth. So they're clearly giving us intention that they're going to, that you have to have it operate at a specific range. And then we're going to do the same thing for a spring mass. So let's remind ourselves that first, for each one of these, I'm going to try and put everything up here you should probably need to know. The first thing I think you should probably need to remind yourself is that for all oscillating systems, the frequency is the angular frequency divided by 2 pi. And the angular frequency is something that is specific to different kinds of oscillators, and it's going to have something about the restoring force and something about the inertia. For a pendulum, this is G over L, and for a spring mass, this is K over M. So in each case, we have an expression for frequency that has to do with the inertia of the object and the restoring force. So for a pendulum, that'd be 1 over 2 pi times the square root of G over L. They're saying we're doing this on the Earth, so they're kind of giving us the fact that this is going to be 9.8 meters per second squared, or 10. For a problem like this, it's just like any other problem. I really don't care if you use 9.8 or 10. If it's a laboratory, then you probably should be using 9.8. But for something like this, if you want to just make it easier on yourself and use 10, that's just fine. And that would be fine on the test tomorrow as well. So they tell us the frequency is 0.3. So there's just a little algebra to do here. I see a lot of algebra mistakes in situations like this. I would prefer not to, but hey, you guys make mistakes on stuff like this all the time. I'm going to multiply by 2 pi. Square both sides. And probably cross multiply or some way of getting L by itself. I've noticed this is where you guys tend to make the biggest mistakes when it comes to algebra stuff, trying to get something out of a denominator. This is it. Everything on the right's just a number. And a frequency of 0.3 means it oscillates about, a period of about 3 seconds. So I'm expecting this to be longer than a meter. That's not unreasonable considering the situation that's there. I don't know what this numerical answer is. Somebody want to give it to me? That would make reasonable sense. So 2.75 meters. You're then asked to go through and find a spring mass system with a 1 kilogram. If a spring is to be used instead, what would be the spring constant needed to be able to accomplish the same frequency? So I assume we're talking about the 1 kilogram mass in that circumstance. So it's more or less the same exact problem, except you're looking for K. We still have a frequency of 0.3, but this time we're going to have 1 over 2 pi times the root of K over M. And you're just solving this for K. So I put in the 1 for the mass. I'm still going to have to multiply by 2 pi and square both sides. So 0.3 times 2 pi, all of this squared, equals K. Seems pretty straightforward so far to me. Any questions about this? Okay, there's more to come. Yeah?
No, just about the L. Can you go to the left a little? 'Cause yeah, when you're in that situation, when it's like the arrow is starting, weren't you divided by 10 on both sides?
No.
How do you get that by itself? Use the time?
So if I want to get L by itself, one way to do that would be to multiply both sides by L. And then divide both sides by everything else. that good?
Yeah.
No. All right, so the problem then says we're going to take the whole thing on the moon. If this pendulum were to be used on the moon, what would the period be? If instead the spring with the 1 kilogram mass were used on the moon, what would its frequency be? Well, the spring mass system wouldn't change. Its frequency would still be 0.3 hertz. And gravity doesn't affect the spring mass system. So if I took the 1 kilogram mass onto the moon, it's still a 1 kilogram mass. And whatever the spring constant is, that's still going to be the same for the spring. They're just now on the moon instead of the Earth. They're still going to oscillate the same. So there'll be no change in the frequency of the spring mass system. In fact, that's how you take masses in places where gravity might be difficult to use. You put them on something like a spring and you shake them. That's how astronauts measure their mass in space. They put themselves on like a shake table or chair. It bounces them back and forth, and they measure the frequency, and that's how they determine the mass. Astronauts have to maintain constant monitoring of their mass in space because the opportunity to lose bone density is actually pretty strong because of the lack of gravity acting on them. Now, unfortunately, the pendulum's going to behave different. The acceleration of gravity is different on the moon than it is on the Earth, so your pendulum will behave in a different way. So that one you do have to worry about. To figure out the answer, they wanted period. Period is 2 pi divided by omega, or 2 pi times the square root of L over G. We're going to use the same length, the 2.75, but you're going to have to look up the acceleration of gravity on the moon. Or you have enough information you could probably calculate it, but that would still require you looking up the mass and the radius of the moon. And I throw that out there because we are getting ready to start our full review. Being able to calculate the acceleration of gravity on another body in space is something you're supposed to be able to do. So I'm counting on you either telling me what this value is, looking it up, or calculating it. Did anybody just look it up? What'd you get?
I got 1.62.
Yeah, that's what it is. So instead of using 10, we use 1.62. And that'll work out, give you the period on the moon. That's problem number 7. A lot of these problems. And it's going to have questions where they're going to mix stuff up. So let's start with the first cart. It's attached to a spring. And what we're describing here first is a collision question. So the first cart is not moving. It's 250 grams. And it's at rest. This cart is moving. It's 150 grams. And it's traveling at 0.5 meters per second. There's going to be a collision, and the two carts are going to join together. In so doing, the momentum of the system will be the same before and after the collision. So we have a starting point that looks like what I've drawn there, and then an ending point, which is just before we start to compress the spring, where both carts are joined together. And have some combined velocity. This is a perfectly inelastic collision. The momentum before the collision has to be equal to the momentum after the collision. Everything's given in grams. We should convert it all to kilograms, which means just putting a decimal point in front of everything. I'll make the decimal point nice and big for a mirror so you can see it. Don't want to miss it from like last week. So I'm going to start by recognizing that the momentum of the first car plus the momentum of the second car will have to be equal to the combined mass of both cars times their final velocity. We need to find the final velocity after the collision. That's the first question. Now, I'll be honest, I would probably skip that question if I was writing this for a test to see if you understand that you will need that information to answer all the other questions, but not make you find it first. So I know that you don't believe this, but having them ask this question first is a gift because they're cueing you into what you will need to know for the rest of the problem. So 0.15 times 0.5 is going to equal 0.15 plus 0.25 times the final velocity. This is pretty straightforward math here. Looking at 0.5 times 0.15, that's going to be 0.075 divided by, I think that's 0.4, and that's going to equal V final. This will be the final velocity of the system. I don't know what it is. Somebody work it out for me. Give me the numbers. No one did this one? Not sad.
How did you get 0.5 and not 0.25 on the left?
Where are we talking about?
On the left?
The 0.25 isn't moving, so it has no momentum.
Oh, so you're just doing the velocity times the first mass.
Yeah. MV. It's early morning, isn't it? Yeah.
0.187.
Point.
0.187.
All right. Thank you. Meters per second. All right. So we have the velocity of the system after the collision. You can calculate any number of things from this. So let's start with the obvious. They ask, what is the energy in the system after the collision? Again, I kind of think that that's kind of a gift question because you're going to need that later. So we're talking about kinetic energy. The cars have not begun to compress the spring yet. So all the energy has to be in the form of kinetic energy. So that's 1/2 times 0.4 times 0.1875 squared. That's going to be the kinetic energy of the system. You can get the number, but you're going to need this. It says what percentage of energy is lost due to the collision. That's a different question entirely. You will need the kinetic energy before the collision to figure out how much kinetic energy is lost during the collision. To figure out the kinetic energy before the collision, you're coming back over here to look at the kinetic energy that existed in just the one car, 1/2 times 0.15 times 0.5 squared. This is the initial kinetic energy, and this is the final kinetic energy. They're asking for the percentage of energy lost. If you're going to take any notes today about stuff that was from first semester, this one you should remember. And if you don't, you have to find out how much energy was lost, and then you have to divide by the amount of energy you had. So to find out the percent lost, it's going to be K final minus K initial divided by K initial. And then you convert that to a percentage. You have to find out how much energy is lost and divide by the original amount of energy. Now, if you want to get the next question, which is, what must the spring constant be if the cars traveled 0.2 meters after the collision? Well, this energy becomes elastic potential energy. Well, it's going to be conserved in this situation. So the amount of kinetic energy the two cars have is going to be used to press in the spring. How much the spring is pressed in is going to depend on the spring constant of the spring, but you know that the displacement of the spring is 0.2. So that's how you're going to get your spring constant. Is that okay? Want me to do any more than that? Because the next part, moves on from here. No one seems to care. Look, this is not my problem. Lester, are we doing good? You want the answers here?
Sorry, I'm looking back at the question. No, I think you're good. I just didn't know how to do that.
All right. I do want to that part where it says how long does it take for the carts to return to the equilibrium position after the collision? You should pay attention to that. They're asking for a part of the period. The period would be how long it would take for one complete oscillation. So that would be the cars going this way, then this way, and then back to here. That would be the period, starting from, in this case, where the cars actually begin, which is at the equilibrium position where they suddenly have energy. So one full oscillation has to come all the way back to that equilibrium position from the same direction as before. But you want how long it takes to come back to the equilibrium position the first time. That's just this direction and this direction by itself. That's 1/2 of the period is what they're asking for in that last part. And I am definitely going to ensure that that shows up on the test, that you understand the portions of an oscillation. The last part of the problem is replace the whole thing with a pendulum. Yep, it's no big difference there. The only difference would be that instead of we have the spring there, the problem would look something like this problem where the period. You get your K from here. All right. Is that good for you?
Thank you.
You're welcome. Like this. The cart's attached to a string here. And this cart is still moving at 0.5 meters per second, still has the same mass. And during the collision, the two carts join together and swing upwards, something like that. And we start the system into simple harmonic motion, but as a pendulum. Same problem, same kinds of things. You'll have to find probably the angle here instead of finding out, or you'll be given the angle and find out, something about the length of the string or something like that. There's any number of questions that can be asked that are super similar. You just have to be aware that in this case, the kinetic energy that we have before is going to be set equal to mgh or mgl1 minus cosine with a pendulum. Everything else in the problem would be the same, but the pendulum part changes the nature of how you deal with the energy. And also, period for a pendulum, 2 pi times the root of L over G as opposed to... Any other homework question you want me to talk about? Yeah.
Can you do number 8?
Is that the one with the pendulum and the pin? Let's consider just drawing a few things here. This is one side of the pendulum. Make this kind of our equilibrium position, but also have it represent where the pin is, so that when it's on the other side, something like that. Does that look about right? And then there's the point at the very bottom just before. So trying to get all the pieces kind of in there. So here the velocity is 0. Here the velocity is 0. This is the max angle on this side, and this is the max angle on this side. They are not different, but the amount of gravitational potential energy here has to be equal to the amount of potential energy here. So when you compare those two, the two angles won't be the same. And both of those have to be equal to the amount of kinetic energy here. But don't forget, there's got to be an upward force of tension that is greater than weight. In fact, we've done this problem before. So I'll remind you, the net force has to be equal to MAC, and it has to be upwards. So that means tension minus mg has to equal mv squared over r. This doesn't change at the bottom. This doesn't change at the bottom, and this is the same at the bottom, but r is going to change the moment it hits the pin. Before it hits the pin, the radius of curvature is L, and then after it hits the pin, the radius of curvature is L over 2. If this number is getting smaller, this whole side is getting bigger, that means the tension has to increase. That's a lot to have to explain, but I think it's within the wheelhouse of our exam for you to explain that. Now, The most pedestrian part of this is coming up with what the period of the system is, and it's 2 half periods, T1 and T2. The first period is 2 pi times the root of L over G plus the second period, which is 2 pi times the root of L over 2 over G. I mean, there's some combining to do there if you want. I think you guys could probably handle the algebra. It's not a whole lot. Start with number 3. And it says Jane runs along a level surface at 3 meters per second. She encounters an 8-meter long rope that she's going to use to swing out over a lake. What maximum angle does the rope make with the equilibrium? If the rope has no mass and she grabs onto the rope while it is in equilibrium. All right, so that's the whole question mark. And then what is the period of her swing and how long does it take for her to make it to the point where she stops moving? All right. There are a variety of other questions that could be asked here, especially since we are at the end of the year. I think it apropos that I bring up other things that I would likely ask if I were writing a test related to this material if I was trying to get you prepared for the AP exam. And since that is clearly what I'm trying to do, let's make sure you understand the full scope. So let's start with the setup of the question. I've got a 8-meter long rope, something like that, and Jane's about to grab the rope, and then we'll have a situation here where after grabbing the rope, she'll swing out to some angle. I'm looking at just these 2 states of the problem. Does this look like a good setup for you guys? We good to start? First, there's a lot here that wasn't asked that could be. And so I'm going to add questions to this as we go. And I might not work them out all the way, but I think you should be preparing yourself for what will be on the AP exam. In this example, they never bring up the tension in the rope, but that would be an excellent question at the bottom, because when she first grabs the rope, that instantaneous moment that she grabs the rope is perfectly vertical, but there has to be an unbalanced upwards force that's greater than gravity in order for her to have centripetal motion. So for that moment, there's this T minus mg equals MAC. Sound familiar to first semester? Because I really hope so. You put that together, you get T minus mg equals mv squared over r, where that becomes the radius of her curvature for her circular motion. Now, the moment she begins to swing, the tension changes because her speed is changing. But this instantaneous moment is well within the scope of our problem. Remember how every problem asked that had this in it always talked about the bottom of the swing, or when the roller coaster car was at the bottom of its circular motion? They either ask at the very bottom or the very top. This is why, because you can work the math out. So I don't ask it in this question, but there's no reason why it couldn't be on this question. I do ask it a little bit. I'm not sure if I do or not for the one with the peg, but I talked about it last class period. Let's answer the questions that are asked of us, though. What maximum angle does the rope make? That's a conservation of energy question. There's kinetic energy here when she first grabs the bottom of the rope. When she swings upwards and comes to rest, it's all gravitational potential energy. But they don't ask about the height. They ask about the angle. And I believe we've talked about this before, and you'll have to correct me if I'm wrong, but we have a method for dealing with the height in terms of the angle, and it replaces the height with L times 1 minus cosine theta. Do I need to review where that comes from? Okay, so I saw 3 heads go like this. That seems to be enough for me. If you didn't get your thoughts in on time, raise your hand and I'll go over it. Okay, so I will go over it. I'll come back to this. I think that's how you're going to figure out the angle. Now, I don't want to do all the math because I don't really care that much about it, and you do. So 1/2 times 50 times 3 is how much kinetic energy we have, 1/2 mv squared. And that has to equal, 50 times 10 times 8 times 1 minus cosine. Right. L is the length of the rope, and the rope was 8. You can use that to solve for theta. I would if I were you. Be concerned. If you work this out, it's plausible that the person is running so fast that they can make a loop. Now, it's unlikely, but if they're running fast enough where they can make an entire loop, do you guys understand what I mean by a loop? Then you'll find that there is no angle that fits here because they go all the way around. So that's a possible circumstance. Just be aware of that. So if your number looks funky or you have to take the inverse cosine of a negative number or a number that's greater than 1, you've probably got a situation in which there is no angle. So this is the kind of thing where that's possible. So I don't know that I would do that on a test, but I want you to kind of see that is a possible outcome of something like this. Now, I doubt that she could run fast enough and hold on enough to make that happen, but, who knows? Perhaps I underestimate her capabilities. The next question is, what is the period of her swing? That one's pretty straightforward. You don't have to do anything in this problem to get that answer. None of the energy stuff. Period of her swing just comes from that. We know that it's a pendulum that has a length of 8 meters. So you can get the period right from there. But then they ask another question I think is more important. And I think they would ask the last question without asking the period question. It says, how long does it take for her to make it to the point where she stops moving? So we're only demonstrating this to this. So that's what they're asking about. And you need to know how much of a swing that is. And that is 1/4 of a period because we go from an equilibrium position to one extreme. If you look at your oscillating thing, that is 1/4 of one complete oscillation. So the time it would take would be 1/4 of the period. All right? Do I need to do more of this problem? Like put numbers into the blanks, or you guys can do that? Good. So I don't want to do any more. This question, you should ask yourself about this, and let me draw it real quick, just so I have some reference. So the top represents equilibrium, but then the mass could be in a state of oscillation where it is pushed off to one side and maybe oscillating. So if this is equilibrium, then it's been displaced some distance x. Okay. Can we all agree that this system will oscillate? That there'll be motion back and forth? All right. So the next question that we have to consider is, would this object be in simple harmonic motion or just harmonic motion? And that's a more complicated question. It's difficult, I think, at this point for you guys to fully understand what makes something have simple harmonic motion. So let me make it clear. For something to be in simple harmonic motion, it must be experiencing a Hooke's law-like force. I'll say that again. For something to be in simple harmonic motion, it must be experiencing a Hooke's law-like force, which means the restoring force must be proportional to a negative sign times a constant times displacement. We've talked about this a number of times, but you need to evaluate your system and see if these criteria are met. If they are, whatever this is becomes the value for K in all of your formulas. So we know that we have the angular frequency, which is the square root of K over M. We have frequency, which is, angular frequency divided by 2 pi, or 1 over 2 pi times the square root of K over M. We have period, which is 2 pi times the root of m over k. There's x max times the square root of k over m equals v max. And there's x max times just k over m equals a max. These are all the different things that we've associated with simple harmonic motion. In every one of these, that constant shows up. If you're looking at a situation and you can phrase the situation in terms of a negative sign, a constant, and a displacement, then it obeys simple harmonic motion. So, I want you to consider what we've just done. We have just displaced the object to the right. Can you tell me the forces acting on it? Just draw a free body diagram for a minute. What would be a force acting on the box in the bottom situation? Nothing. Interesting. So you can't tell me any of the forces that act on the box? That's a disappointment. All those student leaders out there, and I can't remember how to draw a free body diagram. That's sad. Emily, you had your hand up first. Why don't you give me one of them? Which spring?
The one to the left, K1.
What direction is it pulling on the box?
To the right.
So K1 is pushing this way? Okay. I don't think it would be.
No, the other way.
I think it'd be the other way. I think because we've pulled the spring outwards, it would try and pull it back. So I think spring 1 would have a force this way. And let's call that force from spring 1. Okay? Any other forces acting on the box? Sir?
The other spring will be pushing in the same direction.
All right, so because the spring is compressed to the right, how many of you agree it would also push to the left? I think so too. So force from spring 2. And clearly there would also be gravity and normal force, but they would be in the vertical direction and they are likely to sum to be 0. These seem to be unbalanced, would you agree? So I'm going to have the force from spring 1 plus the force from spring 2. Do you want to make the right positive or do you want to make the right negative? Make the right negative? Fine. If we make the right negative, then to the left is positive, and that means these two forces are positive. Now, each one of them comes from a spring. So, how much was spring 1 stretched? What distance? Yeah? It was stretched negative x. So the force from spring 1 is going to be equal to K1 times negative x. How much was spring 2 compressed? Back table. How much was spring 2 compressed? X, you sure? I'm going to say negative x because it was pushed in the negative direction. Okay, everybody following so far? All right. Have I done anything weird here? Now remember, we want to see if our force in our system equals a negative sign times a constant times a displacement. So I'm going to factor out the negative sign. I'm going to factor out the x. And what I'm left in the middle is K1 plus K2. Do we have the conditions for simple harmonic motion? Do we have a negative sign times a constant times a displacement? It appears we do. This is a constant. So anywhere where I saw k earlier, I can just put K1 plus K2, and that'll be how my system behaves. For example, the period of this system would be 2 pi times the root of m over K1 plus K2. So that's our new constant. All right, that's how it's done. All right, that was number 5. So this is number 6, but number 6 refers to number 4. And number 4 is a spring mass system, and I don't really have to draw this out, but there we go. The mass is 2 kilograms, 18 newtons per meter.
I was drawing the graphs for the number 5 one instead, so
Oh,
I didn't.
okay.
Sorry.
No, you're fine. So we're good then?
Yeah.
Okay. Then I will stop talking about number 6 unless somebody else needs it. Yeah. What's next?
We can talk about number 8.
Sure. I'm going to draw it, then I'm going to go take... I set it up again just so we have it, but let me draw it out. I want to put a vertical line in first to kind of be the guide for equilibrium. And I'm going to mount the pendulum here. So let's assume that I want to draw this so that's as accurate as possible. So give me a second. I'm trying to make it accurate. Well, my goal here is to make sure the length features correctly in proportion to everything else. So I'm not trying to get exacting detail, but I'm trying to make sure that I can demonstrate something with this description. So all right, I think that'll be sufficient. So 3 states of the problem. Over here, and it's hitting the pin right there, so something like that. And it's traveling from here to here to here and back again. So the first thing I want you to kind of recognize is that although it conserves energy, in order to be at mgh on this side and the same mgh on this side, you have to take into account that the length changes. Here, the length is L, but here, the length of our pendulum is L over 2. So on this side, the potential energy will be based on L times 1 minus cosine theta. And there's the theta on the left side. But here, this will be L over 2 times 1 minus cosine theta on the right side. So this is theta on the right. The 2 thetas will be different. They have to be. The theta on the right has to be bigger than the theta on the left to compensate for the fact that the length is different. So that's the first thing I want you to do, is to recognize that. Here's something else that you may not be thinking about, but you probably should be. I don't ask about it in the question, but I probably should be. At this instant, it has the same velocity no matter which direction it's traveling, which means the velocity just before the string hits the pin has to be the same as the velocity just after the string hits the pin. Let me say that again. It seems obvious to me, but the velocity just before the string hits the pin has to be the same as the velocity just after the string hits the pin. It's conserving energy, so the kinetic energy stays the same, both before and after it hits the pin. So the velocity stays the same, just before and after it hits the pin. But listen closely. Just because the velocity is the same doesn't mean other things don't change. Right when it hits the pin, the tension in the string has to change. Because even though the velocity is the same on both sides, the net force has to equal mv squared over r. It's in circular motion at the very bottom. And r suddenly changes, which means r becomes half of its size, requiring twice as much force. Right? It goes from mv squared over L to mv squared over L over 2. You work the math on that, the 2 gets popped up to the top, and you get twice as much required force, which means the tension has to increase dramatically. And that's because suddenly it has to make it turn over a much smaller radius at the same velocity. So the tension changes right when it hits the pin. Changes a lot. I'm bringing this up because that question wasn't asked. It probably should have been. If I'm trying to make sure I expand the exam to talk about and take into account the whole year worth of content, that's the kind of thing you should be thinking about. Now, on this side, the period is 2 pi times the root of L over 2 divided by G. And on this side, the period is 2 pi times the root of L over G. But it only does half of this period and half of this period, because it does 1/2 on each side. So if you want the total period of the system, it would be T total would be 1/2 of 2 pi times the root of L over G plus 1/2 times 2 pi times the root of L over 2 over G. That would be the period of oscillation. Right? It spends half of the time with less period. You can actually do some stuff there. You can do some factoring and things. I don't care too much. I don't know if you guys know how to do factoring here. I mean, clearly you can do 1/2 times the 2 and get rid of the 2's and all those. You could factor out the pi, but you could also factor out a square root of L over G. And I don't know if you guys have that as a skill set for algebra yet. I've watched your algebra, and a lot of times you would probably finish here and think that you're kind of done. If you're really trying to hone your skill so that you'll be better at maybe more complex stuff, you can break this up into 2 fractions that are multiplied by each other, and then you could factor out the parts of this that are the same. Oh, I don't know why I have a minus sign, maybe a plus sign. So, I mean, I don't know why that's an M, that should be a pi. There. Now Mr. Shelton's algebra is all cleaned up. This would be more or less acceptable, but you can see why this has some benefits, I think. This once. So do me a favor, guys, write it down. I would use a ruler to write it down, because what I find is that if you can do a good job of making this to scale, you will probably understand it better. So I've ensured that I have a line that is the same length both times. So if you're trying to draw this, pick a length and draw the same length line twice. So if you don't understand what I'm saying this is L, and so is that. Now, we know we have this problem with, Jane hanging here. But the real thing is about the triangle that's made here. This is how high she's swung upwards from the reference level. So I want to kind of project that backwards. So I'm going to draw a horizontal line here and mark that this must also be H. Everybody see that okay? And I've drawn that in such a way as to make this a right angle. So that right now, in the middle of this drawing, there's clearly a right triangle here. Are we seeing the right triangle? This is the angle in question here. This is theta. This is the adjacent side. And looking at the geometry, the adjacent side would equal L times the cosine of theta. Just throw that anywhere. Now, if you look at this picture just right here, it seems clear to me that L equals A plus H. So H equals L minus A, and therefore H equals L minus L cosine theta, which, as described before in class, now going on at least 4 times, that's how you compare the angle with H. So I assume if I walk around right now, I will see this geometric perfection drawn carefully on everybody's paper, especially the ones who put their hands in the air and ask me to do this. I don't want to test that theory because I watched who wrote and who didn't.